I am presenting work conducted with Dave Lees and Tony Colaprete, Darlene Lim. I'm sorry, I'm not actually able to. Okay, pardon me. So the four of us work together as a team, bringing different areas of expertise and also doing additional work to function as an interdisciplinary team. We have different science backgrounds, and together we have an array of experience developing and conducting remote operations with instruments in extreme environments on and off Earth. Next slide, please. The Viper mission is familiar to many here, and while its status is pending, in the preceding years we had time to design, evaluate, and develop a work system for real-time science decisioning within collaborative science operations, the components of which are shown in this presentation. And I will add that as many know, the status is pending. I am at NASA Ames because we are today doing an ERT. So we do continue to work on this mission. The Viper rover is intended to land in the lunar South Pole and to operate for 4 lunar days. Each lunar day allows for 14 Earth days of continuous 24/7 operations. And the solar-powered rover can move up to 20 centimeters per second on flat terrain, but its actual expected speed with the anticipated lunar surface conditions is closer to about 1 centimeter. Next slide, please. The rover is equipped with a number of instruments to be used by the Viper's science team in the service of their work characterizing the form and distribution of water ice in the lunar subsurface and understanding lunar volatiles for future resource utilization. The instrument suite includes 3 spectrometers, 1 augering and percussive drill, and 9 cameras. Next slide, please. This representation of the Viper mission was created by Viper's mission systems team. And what it does is foreground some of the key activities and time considerations, such as the pre-planned traverse that takes place, that's laid out across multiple science stations. And within each science station, only one is depicted here, but within each science station, there are 3 drill sites. The allotted for activity time in each science station is about 24 hours. We have, of course, the small amount of communication latency. And for this rover, because of that small amount of communication latency, this rover currently operates with waypoint driving, which means that they send a command, the drive team sends a command about every 5 meters. Now, during surface operations, the drive team expects to be informed by Viper science, but Viper's scientists would not be making a traverse decision at every waypoint. For Viper's scientists, real-time science means being constantly and collectively aware of traverse conditions, such as planned and actual paths and instrument data, for the purpose of providing recommendations to the drive team as requested and upon their own collective suggestion. At the start of 2020, we began preparing for real-time science decisioning for science operations on Viper for a winter 2022 launch. This gave us about 2 years to develop, build, test, refine, and about 12 months for readiness simulations. We started with about 18 persons on the science side, and with the knowledge that the group would grow, which it did, double, if not triple. Next slide, please. Our approach to the real-time science system was a design approach that coupled planetary science missions and other project operations experiences with social science. And the social science methods used were primarily qualitative with some quantitative techniques and built on previous applied methods, including work ethnography for collaborative and remote work. And one of the patterns that we identified among the scientists and engineers was the use of prior, current, and even future missions and projects as reference points to shape the development of operations. And while it is true that Viper's science operations would be similar to other robotic and human surface operations, the question was whether a comparison was in fact aligned with the development that was being focused on with respect to the types of remote interactions that were involved, the communication latency, digital work support tools, which of course have changed over the decades, and the activity itself of real-time science decisioning, the experience from the other projects, if it was the same as what was intended to be on Viper. So from the comparative research, one point that surfaced was the difference between collecting and sharing data for post-mission analysis and collecting and sharing data for analysis that was needed in situ during surface operations. So we applied this question at times throughout the development process. For example, in working on derived data products, we would ask the question if and how a data product could be used to shape science during surface operations. The importance of post-mission was very well known, but thinking that through in terms of the current, how it affects during surface, was the harder problem to solve. And so we built the real-time science system for Viper, and change slide, please. And we drew from known practices, and we took the opportunity to add and test new features. And what you see now is the several of the workspaces at NASA Ames from a depiction of. So from late 2020 to 2021, we produced the science architecture. We built a mission science center in proximity to the mission operations center. We called out 14 roles for the science team, 12 of which are in the mission science center and 2 of which are in the mission operations center. And what we did was locate a real-time scientist on the drive team being comprised of the rover driver, the rover co-driver, navigation, and the real-time scientist. Then in order to mitigate or reduce the workload of the real-time scientist who was already at maximum, we placed a science lead in the mock to serve as to have a communication relationship with real-time science, and a second one with the MSC lead. In the MSC, of course, with the scientists leading various themes and the instrument scientists working through the activity timelines, we'd allowed for one person, the MSC lead, to be the primary conduit to the mock. And this was two-way communication. One of the primary responsibilities of the Sci lead is to provide situation awareness to the MSC. Next slide, please. So one more click. I've got a couple of slides here that show some of the tools that we built for providing a collaborative experience, a collaborative real-time experience. When we started the project, there was no interface planned to be placed amongst the scientists, giving them the real-time view, although they were asked to be aware enough to give recommendations. So we had the Lunar Dynamic Science Table. Next slide, please. One more click. Yeah. We wanted to make sure that the various data streams coming in could be seen at the same time by all the scientists on shift. Next slide, please. In order to complete what they let us know they would be working on during surface. So these decisional data products for real-time science analysis and operations were called out by the individual scientists, then put together, shared across the science group. And we carefully, intentionally built overlap in awareness on data products. Next slide, please. While also keeping what was separate and a separateness and responsibility to scientists who could be the maybe the primary SME when it comes to particular techniques, analytical techniques. This is an example of the decisional data flow architecture that we built for each science analysis process. And the one you see here is for geostatistics and analysis. Next slide, please.
1 minute, please.
This is the MMGIS map tool that we brought from JPL that was developed to provide awareness for location on Mars, and we adapted it for the moon. Next slide, please. And if you would click a couple times, the full slide will appear. This is to indicate our constant questioning to ourselves and to the team of how many representations were being placed into the context such that you are monitoring that you aren't overburdening what you can do in the moment. Again, with the how does this affect what's happening in the real time? Next slide, please. And I bring us to a view of the integrated real-time collaborative workspaces. For Viper, we have scientists in the Payload Operations Command Center on the far left, scientists in the Mission Operations Center in the middle image, and scientists in the Mission Science Center on the far right. Next slide. Thank you.